Am I audible? Can people confirm this if I'm audible? You need to reboot that in the next time. Take your time, no issues. So anyway, we'll get started. Sorry for the delay, guys. Okay. Welcome all. This is Sandeep Deshmukh. I'll be presenting the data file ingestion using Apex today. So today we'll be covering what are the challenges in big data ingestion, and then we'll be also covering how do we design an application using Apex that will consist of input and output components, and we will see how these components can be built as different small functional units in Apex. Then we will try to do a small demo of one of the utility that's available for use by Datatron, and then we'll summarize. Okay, for those who are the first timers for Apex, or those who are not having a background in streaming, let me give you a very quick 1 minute background of what Apex programming model is. Apex is a streaming platform, and there are different components that are there. The first component is the operator, and operator is a function or the business logic that will be there that you will be using in your application. The data will be flowing through the filter. So all you have to do is process the data, and that data will be passed on through the stream. So we have the filtered stream or enriched stream. These are basically the data carriers which will connect the data or carry the data from one operator to another. And then there is, as a whole, when you connect the operators using the streams, you get a DAG, and that's we call it directed acyclic graph. There cannot be a cycle in the graph. And one operator can have multiple instances that can run in parallel, so that you can achieve a large-scale parallelism using Apex. This is a general streaming paradigm that we use in Apex. What is ingestion? Ingestion is a process of obtaining, importing, and processing data for later use of or storage in a database. And in terms of big data ingestion, is just something additional. That's like we have to discover the data sources, because in big data typically you will have lot many sources than the typical one or two which used to be in the earlier days. Then we need to also import that data and process it and send it out into durable data stores. So our today's webinar is focusing on the storing this data into a durable data stores, typically the HDFS or file type of stores. So what are the challenges when we have to copy file at a large scale, file copy at the scale? So petabytes of data that we need to copy, it's not straightforward. The first and foremost is the failure recovery. How do you do that? Then there are challenges when you have to copy big files in parallel. Let's say you have file of the order of few terabytes, and then how do you copy that parallelly? If we try to copy the file serially one by one, let's say a terabyte file, it takes maybe 4 or 5 hours or even more. But if you try to do it parallelly, you can do it in a lot lesser time, maybe 15-20 minutes or so. The other challenge comes in when you have very large number of small files. The typically case comes into picture when you have small files which are like few KBs, and now you want to copy them. If you have typically a job that is spawned for smaller files, then it will be like the setup time for invoking file copy for this particular file will be a lot more than the actual file being copied, the time taken to copy this file. So that's another challenge. Additionally, you can have processing requirements like encryption, compression, and compaction. So there are many such challenges. I have listed a few key things, and we'll see how we can address them using Apex. So the DAG components that are typically there in any ingestion is we have a read data component where you typically connect to the input source, read the data. Optionally, there will be processing, and then you write it to a durable store. In this webinar, we will not be considering the process step. We'll have a separate webinar to cover that, and we'll be focusing on the read and the write data part. Now, when you design any file copy solution, you don't want to have different application just to copy from HDFS or from S3 or FTP or NFS or any such file type. So our first need is we should have the independent of input type of design. It should also scale to copying large files like terabytes of size or even bigger. At the same time, very large number of small files. Your performance shouldn't change just because of these are the different use cases, and design should be same for both the use cases. Optionally, you should be able to configure the bandwidth, input bandwidth that you would like to use for this application. Okay, so let me just give you a first very basic idea of how any streaming application is to be developed, irrespective of whether it's a file copy or something. The basic idea is we would like to achieve parallelism and scale by splitting the overall bigger functionality into smaller units. And then these smaller units can be executed parallelly, one after another, and get the complete task done. In this context, our first task is basically file splitter. The idea behind this is the purpose is to break the whole task into smaller subtasks. Let's say you are scanning the input directory, and then say there are lots of files and there are multiple directories inside. How do you tell the next person or the next operator, as we call here, to do smaller tasks at a time? So the work of the file splitter is, in case the files are big or the whole task is split into smaller ones, and pass those smaller tasks to the next operator. So as the step says, we have to connect to the input and then scan the data and then create or assign smaller tasks for the downstream operators. That's it. This will not actually copy data. This is just creating smaller tasks. The next operator, the block reader, that works on the subtask given by operator 1, the file splitter here, one at a time. So it is not aware of the bigger picture as a whole. It just knows that, okay, I am given this one subtask and I want to do that. So let's take an example. I have, let's say, 1 GB file and I want to copy it. Let's take it a 1 TB file because it makes a huge impact. I have a 1 TB file and the file splitter is saying I'm going to copy 1 GB at a time, break it into smaller subtasks of 1 GB and then tell the block reader to do that. So block reader is going to take that task of copying 1 GB file. Just don't know how big the file is, but it just knows that, okay, I have to start from this particular start point until this end point of 1 GB and read from the source. So it has to first connect to the source and read data one by one task at a time, and pass that data to the downstream operator. And here the downstream operator is the file writer, which will write that data onto the disk. Okay, so we have a file splitter which creates smaller tasks, block reader which does the smaller tasks, performs them and gives the data to the next file writer. This is a very simple design that we have, right? So the file splitter giving, if we come into the details of it, the file splitter is giving the block metadata. The smaller task we call, we name it as the block metadata. So it has to give the information of the smaller task, that is the block that it needs to copy. The block reader acts on it, gets actually the data and give it to the file writer, and file writer will just write it. Now in this case, when you have to say write 1 TB of file splitter is going to emit block 1, that is the first GB of block metadata, then the second GB, then the third, fourth, fifth, sixth, like that. So it's going to give the block reader instructions to read these data one after another in sequence. And all FileWriter has to do is to append that incoming data based on the file name and create the original file. This is a very simple design. But let's get into what are the challenges in this. So the first challenge is, in this case, reading files in parallel is not possible. So basically I would say, if a particular file is 1 TB, can we read it in parallel? Well, that is not possible. You can have multiple files being read parallelly and written parallelly, but one particular file cannot be read parallelly. Now let me explain why. Let's say I have two block readers which are reading the same file in parallel. So the first block reader is reading the first block, the second one is the second, again the first one will read the third, the second will read the fourth. So alternate ones. Now when the block one reader is being written by the file writer, the second block reader, whatever it is reading, you have to keep that in memory. So there is a sequencing issue. Moreover, output place like HDFS file writer, you have to just append, and you would like to not create intermediate things. So given that, it becomes a challenge to read these files in parallel. The second big challenge becomes the failure recovery. So what happens is, if you have this data in memory, and typically in any streaming application, there is a checkpointing. After a certain period of time, you would like to save state of the application so that in case there is any failure, you can recover. With so much of data, you cannot keep this entire data in memory. And when you write it, actually you are losing that data from the system as a whole. And if there is a failure, what happens is you have to restart writing that file at the output. You cannot just start in between. You need to keep some data in memory for that, which is not possible. And given that, failure recovery becomes a hard problem to address in such cases. Any question which we can address now, or we are so far fine?
Yeah, so far we are fine.
Okay. So there, now we have additional component called the synchronizer. So here the task of the synchronizer is to check for completeness. And what have we really relaxed is that the block reader can read things in parallel. And we save the intermediate blocks that are read by the block reader by the file writer. So it will save it somewhere onto the local HDFS and tell synchronizer that this block is available with me. And synchronizer will check for that file. If all the blocks are there onto the disk, sure it's there, it will say fine, I have that data with me locally. Now please go ahead and recreate the file. So basically we are asynchronously getting the file and storing it as an intermediate place, and then telling the operator ahead, the downstream, that please go ahead and now recreate the original files. This way we can achieve parallel block reading, and even in case there is a failure, you don't need to worry, because you are just reading and writing the blocks. In case there is a failure, just reread the block and write it. You have not started recreating the file, so you can recover very well. So this would be the DAG that will look like. So we have the file splitter, you have parallel block reader and block writer, and then the synchronizer. Here the block reader and the block writer are in a rectangle. That means these two entities are connected to each other very closely. In Apex terminology, we call it as a thread local thing. So what happens is this data is passed on from block reader to the block writer directly without being going through serialization and all. It's just shared directly within a thread, and hence it gives a lot of performance boost. And the block writer will write it and tell the synchronizer that yes, I'm done with this block. Now in the center there is a file metadata connection between the file splitter and the synchronizer. Now this is where this is what the file synchronizer needs to make sure the file is completely read. So the file data contains the information is required to make sure this is done. We'll get into that pretty soon. So let me now get into each of the operators that we have discussed. Let's get into each of them and understand their functionality in depth. So the first operator is file splitter. The functionality is scan the input files or directories and create smaller subtasks. That's the basic functionality. And the parameters are we need a list of input files and directories from where to copy the data. Whether we would like to copy the data recursively or not, that's again a boolean. The polling interval is actually, it will be yes, no, or it can also be the polling interval, the time when you would like to rescan these directories. So the options here are we can say just copy once whatever is there and exit, or you can say keep polling and see if there are new, just reload them again. And optionally you can specify the bandwidth that you would like to utilize for reading. What it emits? First, it emits the block metadata, which is passed on to the block reader, and that is where we say the smaller tasks that subtasks that are created by the file splitter. The file metadata is the overall bigger information that is passed on to the synchronizer to understand what the bigger file is. So here is an example: the name of the file, then you have the size of the file, then you would like to give the relative path, because if it's a relative copy and you want to reproduce in the same relative path at the output, you need to give what's the relative path of the file in the input. Along with that, you give what is my subtask IDs 1, 2, 3, 4, something like that. These are just the sequence numbers which can be used to create the block IDs and eventually give the list of blocks that constitute this file. And the block metadata, as you can see, it will contain the block ID, then the start position and the end position. Here the block size, we are considering it as 128 MB, which is currently the default HDFS block size that is being used. We'll see why later towards the end why this 128 MB is a bit useful number. You can change it, but that's the default that we'll take it up. And then the file URL where you would like to read this data from. So the file metadata has the list, the block IDs, which is what is used by the synchronizer to make sure all the blocks are read completely. That's the information that is read. The block reader takes the smaller task in terms of block metadata, and it reads block from remote location and will actually emit the data. That's its main functionality, and the parameter will be where to read that data from. So if it has to read from an HDFS cluster, it will give me the HDFS cluster where name node basically where I would like to read this data from. Additionally, it will also pass on the block metadata as is to the BlockWriter. The BlockWriter will get the data and actually write it onto the disk. So it also knows the block ID associated with that data. So it will save that with the name of the block ID. And for the block metadata, it's a pass-through information that it will send to the block, to the synchronizer, which will be used to confirm that this block is there. And key part here is it saves data in apps directory. Now, what happens is for every application that is running in Apex, there is a directory dedicated for that application, and this blocks data that we are saving will be saved in that directory, and this information is can be later used if you want to stop and restart this application later. What happens is then you can restart from wherever you left. You don't need to restart everything afresh. So let's say 1 TB file is what you're copying, and 700 GB is already copied in terms of blocks, and somehow there is a crash or there is a failure and you would like to now restart your application from that. You can use this information because it is still there in the apps directory. You can use this and can start reading from where you left, and that's a pretty good feature that you can utilize. You don't need to restart fresh every time. The synchronizer that gets two ports, the block metadata and file metadata input. So all it has to know is file metadata. It knows what are the blocks to expect for a particular file, and then just match it. And this file synchronizer can work on multiple files at a time. So there's no restriction that you can read one file at a time. You can have hundreds of files being read parallelly by different block readers. It just will try to check for the completeness of the file, and once that file is in, it will just trigger and say to the downstream operator, yes, this is done, this is the file metadata, just go and merge it. So this is how a reader block will look like. So you have the file splitter, the block reader and the block writer, and then the synchronizer. This is what is the bigger picture when you are reading the data. The output side, we have a pretty simple operator here. It takes the file metadata as on the input string. So this is what, when the synchronizer commits that, okay, all the data is with me, please go ahead and recreate this file. FileMerger will get that information, get these blocks one by one, read them and recreate the final file. So basically, for a generic purpose, it will be reading these blocks in sequence and appending them at the output side. The parameters are you get the output directory where you would like to create that, and also if you would like to overwrite or not any existing file is there. Now, so what happens, the typical thing that happens in this case is you already have a copy of your data on HDFS, and if you are doing the serially read and write of these blocks one after another at the output side, it's quite time consuming. Let's say you have a 1 TB of file, just recreating that file will take hours. So there is an API in HDFS that comes to your rescue here. So let's say you have these different blocks. This is B1, which has 3 replicas, B1, B1, B1 in blue color. There are 4 data nodes and you have these 3 replicas. Same with B2, B3 and up to Bn. Now all these blocks are written by the block writer in the reader phase, and there is a concat API which you can use to create a file as shown towards the right side. So if you see the data node picture, it's not changing, but it is connecting the inodes that are being used here and creating a file which will consist of block 1, 2, 3 up to n. But there are some, I would say, the constraints where this can be utilized, and those constraints are that all these files or blocks that we are merging should have the same replication factor. They should be on the same HDFS cluster, and the files should have the same block size. And all the files should be, except the last one, should be of the multiple of the block size. So if you can see, the nth block could be of the smaller size, but rest of them should be multiple of the block size. Then only we can do this. And typically in today's world, the destination is HDFS quite a lot. Hadoop lib is quite common, and you would like to just get data and save it as a one or more copy there. So in that case, this is a very useful case. You can read parallelly and just in a split of a second, you can merge it. So let's say 1 TB file, typically if you're reading serially, will take maybe 3 or 4 hours. Here you can just copy it, maybe 15-20 minutes, create those blocks, and within a second or even less, split of a second, you have the file ready. That's quite extremely useful. But for protocols like FTP and all, there's no option but to do a serial merge at the destination. So the whole DAG looks something like this. You have the file splitter, block reader, writer, synchronizer, same as it was, and then you have the FileMerger So the other features that typically are there, so are the gzip and the LZO compression that you can have, then the encryption using PK and AES, and then compaction, and the optional I would say processing of dedupe and dimension computation. So these are the features actually we have in an utility called DT Ingest. It's a free to use utility available for download from Data Torrent website along with the Data Torrent RTS platform. It comes as a pre-built utility, and whatever we have discussed is pre-packaged there, and you can just download and use it right away. Okay, so we'll go through a quick demo on that, and meanwhile if we have any questions we'll take them up. So maybe give me a minute to set it up. We had some setup issues to start with, so maybe need 30 seconds or a minute to set it up, and meanwhile I'll answer the questions if any. Okay. Any questions so far? Then I can get into the demo. That's good. We have the connectivity right away.
Okay, so I think this is a good question. So the question is from Rudresh Shah. So the question is in real HDFS scenario, when we copy the big files to HDFS, it is the split and distributed across all data nodes. Then why do we have a file merger to merge these files?
So basically, let me rephrase and understand the question. So basically, when you are copying this, it is already distributed, right? But on a data node, or if you do a LS, each of this split will have, when you write a BlockWriter, in our case, it will have its own file entry. But what we want is a one single 1 TB file that needs to be given as it was at the user side. So from the HDFS storage perspective, it remains the same. There would be still smaller, I would say, blocks spread across, but we are just stitching these blocks together to give you a view of a single file. Right? Does that answer, Chinmay, make sense? Any other question? Okay. So you just go through the demo. So this is the app that is pre-built with the Data Torrent RTS platform, which is based on Apex, the open source Apache Apex platform. And you can download the community edition of this and use it for free. So you need to give a name. So let me give you quick what are the input types. So the utility supports 4 type of file-based inputs: Amazon S3, NFS, FTP, and HDFS, and Kafka and JMS as the message-based input. So for today's session, we will restrict ourselves to the first 4 file-based inputs, and sometime later we'll also be covering the Kafka and JMS part. So in case of S3, the way you need to give input is you have to give the S3, and that's the native S3 in the protocol, followed by the user key and the password, the passphrase, followed by the bucket and the path. So this is the way you specify where you would like to read data from. In case of NFS, it's pretty straightforward. You just do a protocol name file : / and then the /home/username and the path, like that. Same way with FTP, you give the username, password, host port, and the path, and then HDFS. So this is what we will be demonstrating today. So here we say HDFS : / you give the name node, then the port, then let me see, user Sandeep. I've just created a directory called import within the meetup. The filtering criteria is something which you can specify whether you would like to just copy, let's say, the .dat file, .txt file, or .log files. Let's say you have the .log files and some one more type of .dat, and in this task you just want to copy .dat files. So you can filter saying that these are the only files you would like to copy. The execution mode, there are a couple of them. One is copy and terminate, where it's like, say, one-time copy. You start this task, whatever files are there at the source, just copy, and once you are done, terminate yourself. So the app will terminate itself once the copy is done. In the continuous polling, we would like to say that, well, there could be new files coming into the source, so you keep polling this, and you can give your polling frequency based on your needs. You can give 1 hour per minute or even per 10 seconds or something like that. So that will be determined by your needs. If you want to really be very fast in copying and you have small files coming in and you want to always be in sync, keep it as a small number, or you can say few minutes or so. At the output side, as we have selected these files, you have option of copying this into the files, and similar ones, all these fours are there. The way you provide the directory path is similar to the way we do it at the input side. So I'll just use that as is. Yeah. Okay, then you can specify if you would like to copy the data recursively or not. So there could be input directory could have a lot of directories inside. You may want to skip those directories and just copy in that parent folder. So you can specify no there. Right now we're just keeping it default to yes. Then at the destination side, if there are any output files with the same name, would you like to write them or not? In this case, I'm still going with writing, say yes, do override if required. And compact files. Now this is a very useful utility where we can say that if there are a lot of smaller files that you would like to copy, but you would like to combine them into one big file or roll them over for every, let's say, 10 GB or so, you can specify that. So you can specify the delimiter that you would like to have for each of the file, between the files, typically a new line or something like that, and what would be the compaction size that you would like to do. So all this can be configured here, and right now we are not doing that because we are just copying your files, but you can download and try these options. So this one of the purpose and use of this is, if you have too many small files, maybe thousands or more of that type in every directory, your name node will get overloaded. So this functionality will help you reduce those clutter of small files. Then we also have options to compress data using gzip or LZO, and encrypt using AES and PKI things. So if you want to use them, you need to specify the key that you would like to use for encryption. Optionally, you can also provide the bandwidth for this. So maybe I will put it like 200 MB per second or something. Now this is one parameter where you can specify how many parallel block readers you would like to have. I'm just putting a value of 4 here, but you can pretty well make it 32, 64 depending on your input data. The other option is auto, and this is a cool feature that we have. Auto basically means, well, I don't know how much is the need, just decide yourself. And in that case, if the data that is being read is quite a lot and the block readers are unable to cope up with what is being given by the file splitter, it will decide itself that, okay, I need more and more partitions. So in that case, it starts with 1, but the moment it says it feels that there are a lot of work to be done and it's lagging behind, it can auto scale to, let's say, 16, and then it will read all that data with 16 block readers in parallel. Now after some time the data is read completely and there is no data to be copied and it's in the polling state. Now what has happened is all your resources are underutilized. Basically you are just allocating resources, but the task to be done is almost nothing. In case you have selected auto, it will get down to one instance of the block reader and writer, and that can be automatically. You don't need to get involved in this case. Okay, so I'll just save this file. So you can save this configuration that we have done here, and so that the same configuration you can use later if you would like to. Yeah, are there any questions?
Yeah, we have a question from Mahindra.
Yeah.
So what he's asking is when for file splitter the source is HDFS.
Yeah.
So does it take an advantage of metadata present in name node for generation of the block metadata structure?
Not right now, but that's a good suggestion. I think that's we can look into it. But basically, it gets into what is the file size and how would you like to split it up. So this is more at whenever you are doing at the destination side, we would like to split it to a block size so that FastMerge can be enabled. So that's one driving force of split up, but we're not actually taking that information into account.
So Amrit, you had a question. Can you please ask that?
There's one more question, right? That's a good question.
Okay, let's move on to the next question.
Yeah.
So, this is one of the questions asked from Rudresha. So, what if the existing file is getting updated with the polling takes care of the file being updated?
Yeah, good question. So basically the question is what if when what you are copying is itself getting updated. So the polling will notice that there is a file that is getting updated, and in the current design we just recopy that file. Okay, now there is another aspect to it. So typically when HDFS any file is being copied or created, underscore copying underscore is the extension that gets automatically added. And such type of files which are getting generated in HDFS are automatically ignored by DB ingest. So you don't have to do anything unless the file is getting finalized. Okay, and once the file gets finalized, it will auto detect by polling and copy it. Now once the file is there already and it gets appended, it will recopy it. And the extension that we are working on, which will be available pretty soon, where we would be copying just the delta part of the file that is getting added. Now this is typically possible in case of HDFS because HDFS will not allow you random edits in normal HDFS code form. So given that, we can say take it from the input from the reader input saying that whether you would like to do an incremental copy. So it's a user's decision if he or she is very sure that the data that is getting updated is only incremental. We can just copy the incremental part to the destination. And if the data is such that it can be random edit, then the user can turn it off, and in that case the entire file can be copied. Right? So there are different aspects that we can handle differently, but polling will definitely find it out that there are different ways or files that are getting updated. Okay, so let me So I'll just delete the output directory. Yeah. Disconnect. So I'll just delete the output directory so that we can see it's been created again. Okay, so the meetup input directory is what we have as input. Okay, so this is the already existing job. Let me just kill it so that it won't interfere with us, our application. Okay, so let me just reconfirm. So we have the output as meetup output, and yes, we have the input. Okay, so let's go and launch the application. So if you see, this is very easy to configure. All you need to do is give me the input and output directories and do that. So typically, of course, you read it from a remote HDFS cluster. For this demonstration purpose, we are just keeping it locally, and here it goes. We have the yes. So this is what is allocated. Let's see how it looks in the DAG. So this is the same DAG we have seen. There's a file splitter, block reader, BlockWriter, block synchronizer, and then we have FileMerger. There are few other components here which are used for some advanced processing, but basically what we have covered is as is here. Okay, you can see that. Now, this is what is the logical plan, but how it actually is implemented or gets shown. Yeah, this is what it is, right? So this is what is there running on Apex, on the cluster. We have one file splitter, we have specified 4 block readers and writers, then the synchronizer. Okay. So if you see, there is an entity called Unify here. So that is what happens when you have, say, let's say BlockWriter, which are 4 parallelly running, and you want to give that input to the block synchronizer. It will merge all that data coming in from all the 4 BlockWriters to the block synchronizers. Now this entity is automatically added by the platform. As a user, nothing needs to be done. It's just taken care by the platform. And we have specified 4, but we can very easily make it 8, 16 or 32. That parallelism can be done. But you need to be also careful about when you say that, also correspondingly use the bandwidth. Because there is no point in specifying 64 block reader and writer and bandwidth of 100 Mbps. So let me show you what's there in the input first. I think I should have shown it first. So we have a file of 16 gig at the input, and see what's there. We had just deleted the output directory, right? So submit output. So in the output, it will create the path from the directory that you last specified. So if you can see, the file is just got copied, right? It's 8:23. So this is what PST time, and it got copied just now. So what we can do is let's copy small now for the demo purpose. So I'll copy 1 GB file at the input. I'm just doing this from the back end. And now if you can see, yes, it's detected, and now file splitter has already emitted that, and BlockWriter working on it, right? Yeah, and the file is copied. It's pretty fast. I mean, it won't take long. Okay. So any questions? Just to summarize, if you just saw that it's very easy to use, configure and run. We already have seen the architecture behind it, and it's unified for batch and continuous data ingestion, and it can seamlessly handle large number of files as well as large number of small files. Okay, thank you.
So we have one question from Alice. So the question is, when the data is unevenly distributed across data nodes, so for example, if the majority of a file is located in a single node and very less in other nodes, is there a special thing that the ingestion application do? For example, by specifying the block size, does it reconfigure our tune so that it works fine?
From the input side you are talking about,
yes,
right? So if the input side, if there is a particular file which is pretty much one lot of blocks are there on one data node and the remaining are not. So we don't consider anything special as of now, right? So because it's the remote side, we connect and see what's the data size is and then split it into smaller ones. What we can more optimize is the more suitable use cases where this destination of this data is, where this application is running. It's more optimum towards that. When it comes to a remote location, it's finally over the wire that you have to connect, right? So that we are not. But in case, let's say the user knows about similar thing and would like to do optimization, any optimization in terms of block size, all these parameters, advanced parameters are available. At the launch time, you can configure a specific advanced parameter, and a lot of help is available there in the documentation that is available for data ingest online. So you can provide all those details which will make it easy to use or optimize this use of data ingest.
The other question is from Gopal Krishnan. So is it possible to have output type as NFS or only HTTPS?
Just before that, I just reiterate that the slides are already available on SlideShare, and this recording of this webinar will also be made available on the YouTube data torrent handle. Okay, yeah. So just to answer this, yes, we can have NFS, FTP, S3 as output as well. We can have all of these available, and addition of anything new is also pretty straightforward, because as long as you provide this type of functionality we talked about in the start, it is possible. So right now these are readily available destinations and sources.
Okay.
That's it.
Yeah. That's all.
Okay, thanks. Okay, yeah. So thanks for attending this, and feel free to reach out to us if you have any queries. Apex is anyway has a associated Mallar library, which is free and open source under Apache Apex. So you can use these all these modules and components and build your own applications. And this video will be made available pretty soon on YouTube. Slides are already available. Thanks guys for attending. Chinmay?
Yeah. Thanks a lot, guys. Thanks. Bye. Bye.